Hello, guys. Welcome to Runta Solutions. Welcome to your statistics lesson on curve fitting. Now, let's begin. So, you asking what is curve fitting? So, curve fitting is when we sort of feed a function to a data. What do we mean by that? This is like saying you have a data, you scatter plot your data, then you join a line that will best feed that data that you had. Remember, to feed a function is to say what function best represents this data. It could be linear, quadratic, logarithmic, exponential, cubic, and so on. All right? Those are the questions that we can get when we feed a function, right? So we are basically saying sometimes it may be to join the points that are to join the data points. Sometimes it may be to draw a line of best fit, right? But whichever represents the data truthfully, right? So now for this video, we're going to look at bivariate data, which is what you've been doing all along. When you plot graphs, you will be having bivariate data, but of course, so far it has been varying with saying it was only varying with x, right? So we can also look at that in here. Now, we are not going to look at data that varies only with x. We will be looking at data that varies, say, on y or with y, and data that varies with x. That is what we mean by bivariate. Now, the work that we're doing here is adding on or building on from what you had in grade 11. Remember, in grade 11, you had scatter plots. All right. And for scatter plots, if you recall, let me just draw them here. Let me just add a scatter plot. We would have something like this. And then we will say, actually, a line of best fit that would perfectly work is this one here. Right. And this was your line of best fit. Right. So this we did in grade 11. In grade 11, we didn't have the equation of this line. But now in grade 12, we're going to have the equation for this line. And we're not just going to draw a line because of by intuition. Now we're going to draw a line armed by mathematical techniques. Okay. So now this technique that'll help us to sort of give this line an equation, and not just to give it an equation, but to draw the perfect line is called regression. Now this line, which we call the line of best fit, we can now call it the regression line. Okay, but before we proceed, let's see how we can describe bivariate data. Okay, remember guys, bivariate data could be, for example, we could say, let's measure students' performance on mathematics and English and see how they are related. Right, you will find that these one axis is marks on mathematics, and on one axis it's marks of English. This is what we mean by bivariate data. I hope you now get it, that we will be saying, let me say here, so this is English. Let's say you are doing English first additional, INFA, and then you are doing mathematics, and then pure maths, that's what you call it, right? And then when you look at it, you'll be like, okay, if you have a line like this, or maybe before a line, let's say the data points are like this. And what do you see? You see that, ooh, with this one, you're saying, okay, it seems like a student that performs, and you say here, students perform, when a student does well in English, directly they are doing well in mathematics. When a student does bad in English, first additional, they are doing bad in mathematics. So there is a strong direct relationship, and maybe say positive strong positive relationship between English and mathematics, right? This you can say, but hold on. We're gonna say this shortly. We're gonna pack it nicely for you. Okay, let's go now. So now our bivariate data, when we describe it, we will refer to its nature. And when we say its nature, we are saying what function is this forming, right? What function is this forming, right? What function is this forming? So by the function, you know by now that you have done a linear function, let's say exponential, you have done quadratic, and there's more, guys, okay? I will say and so on, okay? Quadratic and so on, right? Quadratic and so on. You follow? So now the nature of your data is when you refer to the kind of a function that your data exhibits. Okay. Now, when we refer to the direction here, this is when we say if it's linear, this is when we say it is a positive gradient or negative gradient. In the same way with exponential, we're saying that. With quadratic, we say that. So basically what we mean, for your data to be with the direction, your data could be positive or could be negative, right? Your data could be positive or could be negative. So when it's positive, we are saying when x increases, y increases. And then when it's negative, we say when x increases, y decreases, right? So for example, with a linear graph, this one here is a positive, this one here is a negative, right? With an exponential, let's say when b is greater than 1, it will be like this, and the other one, when a is negative, it will be like this, right? So these are the things that we are looking at. Okay, so remember here, guys, when the direction of your data is positive, we're saying that when x increases, y increases. When it's negative, this is when x increases, y decreases. So we're using x and y for simplicity, but we are basically saying if one data that is on the x-axis increases, the one on the y-axis will increase. That's when it's a positive relationship. If it's a negative relationship, this is when the x-axis data or whatever variable you're studying on the x-axis increases, the one on the y-axis decreases. Okay. Now let's talk about the strength of our data. With regard to the strength of our data, when it's strong, it'll be strong or it can be weak. So when it's strong, this is when the data closely exhibits a function. Okay, so here data points are closely making to closely to perfectly, guys. Okay, closely making the function that you are interested in. Okay, and then when they are weak, this is when data points deviate, right? Deviate from a function. Okay, so here, guys, we say strong. When it is strong, it is closely making the function to a point that it's perfectly making the function. And then when it's weak, it is still making the function, but it has some points. Okay, some points are deviate. Let me put it like this: some points, maybe it could be many points are deviating from a function. Okay, so this is alternatively, you can say this is when the data does not conform to a function. Okay, all right. Now I'm going to give you examples of how we can use all these. Okay, so let's try this. I'm gonna draw a graph here. Let's call this one y. Let's call this one x. So this one here, let's see, what is it? First thing first, I do see a straight line, right? So it's a linear relationship, right? It's a linear relationship, right? It's a linear relationship, right? So what we can therefore say is, okay, this linear relationship, it's a straight line. A straight line of this form is positive. If you don't understand what we mean by positive, you can say when x values increase, y values are increasing. So this is a strong what? Is it positive? Yes, it's positive because when x increases, y increases. So it's a strong positive. What kind of a function is this? Linear. So it's a strong positive linear relationship, right? It's a strong positive linear relationship, right? It's a strong positive linear relationship. What if it was like this? I do see that we don't have sort of a deviation here, right? We don't have a deviation here. So first thing first, um, since we don't have a deviation, it seems like it's strongly exhibiting a linear graph. So we will say it's a strong, but as x increases, what's happening to the y values? They're getting smaller. So it's a strong negative linear relationship, isn't it? It's a strong negative linear relationship, isn't it? Cool. Now I'm gonna try another one. Again, I'm gonna try negative. So let's try this. Now, the question I should ask you now is this. What do you see here? You see a sort of a quadratic, right? So it's a quadratic relationship. But then, is it strong? Remember when you say it's strong, it'll mean that, it'll mean what? It'll mean, it'll mean that we are saying that the points are confidently forming a quadratic function. But here you can see there are some sort of deviations, right? There are some sort of deviations. So they are not strong, but rather they are weak. This quadratic, normally we'll say it's a frowning one. So if it's a frowning one, do we call it a positive or a negative? It'll be a negative because indeed, imagine a quadratic like this, right? So this will be a weak negative, right? It'll be a weak negative quadratic relationship. Do you see that? All right, good. Now we're going to try another one. Then look at this one here. Look at this one here. Y, X. And look at this one here. What about this one? Ah, first and first, what kind of function is this? It's an exponential function. And talk about the direction. The direction, as x increases, y values are also increasing. So it means it'll be positive. Now, are the points strictly or uniformly, shouldn't say uniformly, are they conforming to a function? Perfectly sure, right? So yes, therefore we'll say it's a strong what? It's a strong positive, right? It's a strong positive exponential relationship, right? It's a strong positive exponential relationship, right? This we can say, right? It's a strong positive relationship, okay? So remember with bivariate, I said we are comparing two variables, all right? Now, this is what we can have. I'm gonna maybe draw two more. So now let's try this one here. What about this data? First thing first, what function is this? We do not know. And then, is it strong or weak? We do not know. And then, what is the direction? We don't know. So we'll therefore say this one, it has no relationship. Remember, guys, if you don't want to say relationship, you can say no correlation. Right? You can say no correlation. Okay, you can say no correlation. Okay, you can say no correlation. All right, so this is how we describe the relationship between two variables. Okay, this is how we describe the relationship between two variables, or how we describe bivariate data. Okay, this is how we can describe them. So this one, it's a strong positive linear correlation or linear relationship. This one here is a strong negative linear relationship. I think by now you guys have an idea. This one is a weak quadratic relationship, right? Or correlation. Whereas this one is a strong positive exponential relationship. Remember, with the strength, for it to be strong, what do you say? You say when x increases, y increases. Or when the variable on the horizontal axis increase, the variable on the vertical axis will also increase, right? This is the direction, right? This is when you say it's positive or negative. But for you to say it's strong, the data points need to strongly conform to a particular function. Like in this case here, they are not really conforming to a particular function. You can see that others is like zigzagging there, right? But we can see just is trying to make a quadratic relationship. So we're gonna call it a weak relationship, right? Now this one here, it doesn't have any deviations. So since it doesn't have any deviations, the relationship will be strong, right? The relationship will be strong. Remember, with the direction, you're looking at whether when x increases, y increases, or rather, when horizontal axis increase, the vertical axis also increase. This is when you say it's positive. When it's negative, the whatever variable on the horizontal axis, when it increases, the variable on the vertical axis decreases. That's when it's a negative relationship. Now, with the strength, we said the points need to conform to that particular point. If it's conforming almost perfectly, you will call it strong. If it's conforming with so many deviations, you will call it weak. Right? Good. Now, if there is no conformation whatsoever, or there is not even a function that you can read from your diagram, there is no relationship. Okay, so in the next video we are going to be quantifying this relationship. Okay, we are going to be quantifying this relationship. We're going to put a number to it. Now let's look at linear regression. Now we're looking at linear regression, and we're going to use a calculator here. Okay, we're going to use a calculator here. So with linear regression, I said to you, we're going to find the equation of the line of best fit. And it's going to help us to draw the perfect line, right? It's going to help us to draw the perfect line. Okay. So the linear regression has an equation that's in this form. Since we said linear, you expect a straight line. A plus bx. Okay. This you find in your calculator. Okay, so your calculators will give it to you in this form: a plus bx. Okay, your calculators will give you these values. Okay, so on the calculator you will find them. However, if you don't want to use your calculator, these values are as follows: the value of a. Okay, maybe let's start with the value of b. The value of b, oops, Okay, let me reduce the font size. The value of b is number of terms, sum of the product xy minus sum of x values multiplied by sum of y values all over a number of terms multiplied by sum of the squares of x values minus close open brackets sum of x values, the square of the sum of x values. Right? This is the value of b. Now, to get the value of a, you will say it is 1 over number of terms multiplied by sum of y values minus b over number of terms multiplied by sum of x values. Right? Now, I want to take you to this part here. I'm going to use a different color. I want you to note something here. When you look at this, you are seeing sum of y values over n. And here, you are seeing sum of x values over n. What does this represent? Sum of y values. This must be the mean of y value. And what is this one? This must be the mean of x values. Alright? So we are therefore saying this a could further be written as a is equal to average of the y values minus b times average of the x values. Hence, average of the y values is equal to a plus b times average of the x values. Right? This is what we can say as well. So, you can manually find these terms here or these parts here. Okay? But you are not required to be using this manual calculation. However, if you are to be asked to perform manual calculations, you will be ensuring that you have x values, y values, ensure that you have a row of x times y, ensure that you have a row of x squared, ensure that you have a row of the sum of x squared. All right? If you can do that, you are good. Okay? So these are the things that you need to pay attention to. Okay? But we are not going to be doing manual calculations. We're going to show you using a formula. We're going to answer this using a formula. So now let's try this. Example. Let's say plot the following. Plot the following on a scatter or as a scatter plot. Okay, as a scatter plot, and draw line of best fit and its equation. So the data is, let's say here, we're gonna say this is the age, and then this is the cost. Okay, so we're gonna say the age is 5, 10, 15, 20, 30. And we're gonna say the cost is 90, 140, 200, 250, 250, 300, and then 380. So you need to decide which one is your x will be on the x-axis, which one will be on the y-axis. So let's say this is the age of equipment, and this is the cost of fixing it months after purchasing. All right. So let's remember this data. So what I'm gonna do now, I'm gonna say this will then be my x and this will be my y. So let's try to plot this. Okay, let's try to plot this. Let's go ahead and plot it in the next page. In fact, let me copy this first. Okay, let me copy this. And then in the next page, I'm going to try to paste it. Okay. I need to... okay. Now, let me remove this y. Okay. And redraw, say, cost. The writing is too big, so I'm just... oops. Let me just move it. I'll write it later. Okay, cool. Let me also remove this. So I'm going to say this was age and this is cost. So I'm going to try to draw. Okay, let me use this. So I'm using a grid. So I'm going to try to draw this. Let's see now what happens. So when we draw this, let's see our scale. We said we will let this to be x and we'll let this to be y, right? So x, I will let it vary with 5, and then y, letting it vary with 50. Maybe it can do us justice. So we need, okay, I'm going to let it vary with 50. So I'm going to say 400. Let me see, 400. Maybe 100 would do. Okay, 100 would do. Okay, 100, 300, 200, 100. Yeah, this will do. Here. And then this, I will let it vary with 10. So it'll be 10, 20, 30, 40. Okay. So here, let's say it's age, like I said, in months after purchase. And let's say this is cost. Because we're in South Africa, I'm going to call it R. Now let's try to now plot this. Age 5 months, the cost is 90. We will say it's here. And then, oh, sorry, 5 months. Oh. Then, okay, 10, 20, 30, 40. So 5, we said it's 90. So 90, let's say it's here. Yeah, 90, let's say it's here. And then we're going to go to age 10 months. It's going to be 140. 10 months, 140. It's, let's say it's here. And then 15, we're going to go to 250. Here was it. 250 is here. Now, 20. Oh, where's 15? Oh, I'm seeing flames. 15 is 250. So here's 15. It's here. It's 250. Now 20 is 300. 20 is 300. Fine. 30 is 380. So let's just say it's here. Okay. All right. Now let me remove the grid. Perfect. And then let me just try to highlight them a bit. Okay. Okay. Perfect. Now, we want to know the line of best fit. So with the line of best fit, it's tempting to say it'll somehow be, I don't know, crossing, I don't know where, but we have to try. Okay. But because we are in grade 12, we are no longer just fitting. We have an equation. So what I'm gonna do now, I'm gonna show you a calculator. I'm gonna show you how we do this on a calculator, not a calculation. Okay, so this is my calculator. What you're seeing here is what's displaying on most of your calculators, guys. This is what's displaying on most of your calculators. So we're gonna show this in our Casio calculator. I believe Casio FX82ZA also does this. However, this is Casio 991ZA. Is it 82 or 991? Somewhere there, but Casio 82ZA and Casio, I forgot the others, but I believe they do this as well. Right? So if you're using one like mine, you simply go to mode, and then on your mode, you then go to stat. It's option 3. Okay? Now you are no longer focusing on variance, you are doing regression. You're gonna go to a plus bx, which is option 2. Option 2. Now you enter your values. As you can see, it is 5 equal to, by now you know, 10 equal to, 15 equal to, and then 20 equal to, you then go to 30 equal to. Right? Now you use these cases, up, down, left, right cases, to fill in the data for the y values. Alright, so they are 90 equal to 140 equal to 250 equal to 300 equal to, then lastly 380 equal to. We have entered everything almost correctly. Let's see, is it almost or exactly? It's exactly. So we are good, right? We are good. Okay, now we can press AC. And pressing AC doesn't mean you're canceling, you're just clearing the screen. Now we're gonna find the value of A. So you're gonna say A shift 1. We are looking for regression, so we're gonna go to 5. This is a regression. We go to 5. Then here is it. What is the value of A? Directly, the value of A, you press 1 and then equal to. So what is the value of A? Let me move this guy here. Now we found the value of A to be 40. All right. Now, once again, we're gonna press shift 1. Even if you press AC to clear the screen is fine. We're gonna look for B. So it's gonna be, we took A. Now we're gonna go to regression once again and look for B. And what is this? We find that B is 12, right? Therefore, the regression line here is y equals 40, right? Remember, before I proceed, it was y equals A plus bx. Therefore, the regression line is y equals 40 plus what? 40 plus 12x. So now to draw the regression line, you can do this. Already, you know the y-intercept is 40, right? You know the y-intercept is 40. So you can just plot the y-intercept there. And then now look for another point. Look for another point. So when I say look for another point, you can take any you can think of. I'm going to take where there's x, I'm going to put 30. So maybe let's try. 40 plus 12 open brackets 30. What do we get? We get 400, right? 30, we get 400. So, let's see. This is 400, all right? So now let me return the grid. Okay, yeah, it was like this. Whether it's 30, it's going to be 400. So check this one out. I'm going to use a blue color here. So here is 40, right? And then the y-intercept, as you can see, it's 40. So let's say 40 is somewhere here. All right. Now, let me remove it. Now, I'm going to join that line of test fit. Let's see. it's starting here, and then but do you see this? Do you see this? So this is the line of best feed, right? Sorry, this is your line of best feed, right? This is your line of best feed, and its equation is 40 plus 12x, right? It's 40 plus 12x. Now, how do you then describe this relationship? This relationship, you will say, it is somehow conforming to a straight line. So it's a linear relationship. And then when x increases, y increases. So if when x increases, y increases, we will therefore say it's a positive relationship. All right? It's a positive relationship. What about the strength? We can say this is a strong positive linear relationship, right? It is not really that weak, right? So it's better to say it's a strong positive linear relationship. All right? Now, this is not all. This is not all, okay? This is not all, but because you don't want this video to be too long, we might need to finish here, but we cannot finish as yet. Now let's go to interpolation and extrapolation. Okay. To conclude this video, we're gonna look at interpolation versus extrapolation. Okay. So we're gonna say what is the cost? One, what is the cost of fixing a 48 months appliance? So this is the question we're going to ask. Just stay here. And then what is the cost of fixing a 21 month or 21 months appliance? Okay. So we're going to answer the questions here. We said our line of best feed was y equals 40 plus 12x. Now we said 48 months. As you have seen, age was on the x-axis, so 48 months. So we'll then say, oh, so this means we're saying 40 plus 12 open brackets multiplied by 48, right? So what is this giving us? I'm not going to use the calculator on my screen anymore. I'm just going to use the one I have on my hand as we speak. It's going to be 12, 40 plus 12, open brackets, 48, close. What is this? The cost will be 616 rands, right? Because we are using the line of best feed. Now, let's come here. Now, what is the cost of fixing a 21 months old appliance? It'll be 40 plus 12 multiplied by 21. So what is this? This is 298 rands. This will cost 292 rands. Sorry. Now, interpolation and extrapolation. Look at our data. We didn't have 48 months. This is extrapolation. Did we have 21 months? Was it included somehow? Yes, it is within the range. So this is interpolation. Okay? This is interpolation. So what are these things? With extrapolation, you are predicting with values outside the data set. All right? This is predicting with values outside the data set. You can say outside the data set or the data range, it's up to you. Outside the data set, or let me just say range. So with interpolation, it's predicting with datas within the data set or range. Okay. So when you're using values that are within the data range or the data set, you are interpolating. Okay. So when you predict with values that are outside the data set or the data range, you are extrapolating. For example, we do not have 48 months in our data set. So that is extrapolation. With interpolation, we can say we can have 28, 21 months. It is within our data set, therefore it is interpolation. I hope you guys got it. Now, with that being said, it's a wrap. I will see you next time. Next time, we are looking at correlation, and that is when we give you the meanings of all these values, where we're going to give a meaning to what we have here, the relationship, whether it's weak, strong, and so on. Okay, with that being said, it's a wrap. See you next time, and bye bye.